The James Webb Telescope has made the discovery of our lifetime, and we might not look at black holes the same way ever again. After several observations and discoveries by the JWST, scientists and astronomers decided to examine black holes with the world's most powerful telescope. The team of researchers used the JWST in a bid to find out what is inside a black hole, and their discovery is about to change everything. So what did the James Webb Telescope see inside the black hole? Could it be alien communities? Join us as we explore how the James Webb Telescope finally saw what was inside a black hole. When astronomers pointed the James Webb Telescope towards the final frontier for the first time, they were surprised at the results it sent back. This gave scientists and multiple teams of researchers confidence in the telescope's high resolution and high sensitivity. And so it was used for more missions. Even the past missions or observations done by previous telescopes were revisited, and the powerful optical telescope mesmerized the world of science as it peered into space each time. Well, it was all a pleasurable rollercoaster ride of amazing discoveries until the James Webb Telescope was directed to observe what was inside a black hole. The entire encounter began when the James Webb Space Telescope discovered the oldest black hole in our universe. This is a cosmic monster observed to be 10 million times the Sun's mass, and astronomers were thrilled to have found this rare phenomenon. The James Webb Space Telescope at JWST, whose powerful cameras enable it to examine the final frontier all the way back to the very earliest stages of the universe, found the supermassive black hole at the center of a baby galaxy 570 million years after the universe's inception. Immediately after the discovery, speculations and theories started to flow in. The cosmic monster might just be one of numerous black holes that gorge themselves to monstrous sizes during the cosmic dawn. This era started about 100 million years after the Big Bang, when the young universe glowed for a billion years. Scientists and astronomers are not exactly sure why these enormous numbers of black holes came to be or how they became so big. The scientists who discovered the newly discovered black hole published their findings earlier this year, although it has not yet been peer-reviewed. This is the first one we're finding at this redshift point in time after the Big Bang, but there should be many of them. The lead study author, Rebecca Larson, an astrophysicist at the University of Texas, made a comment, "We do expect that this black hole didn't just form, so there should be more that are younger and existed earlier on in the universe. We're just starting to be able to study this time in cosmic history this way with the James Webb Telescope, and I'm excited for us to find more of them." Black holes form after the collapse of giant stars, and then they begin to grow by continuously gobbling on gas, stars, dust, and other black holes. For some greedy space-time ruptures, the friction causes the material swirling into their maws to heat up, and they discharge light that can be found by telescopes, transforming them into so-called active galactic nuclei, AGN. The most extreme AGN are quasars. These supermassive black holes are 1 million times the Sun's mass and shed their gaseous cocoons with light blasts that are way brighter than the brightest stars. Because light moves at a fixed speed through the vacuum of space, the deeper that scientists and astronomers explore the universe, the more remote light they cut off and how far back in time they see. In order to find the black hole, scientists and astronomers observe the sky with the JWST's mid-infrared instrument and near-infrared camera. They also use the camera's custom spectrographs to break down the light into its component frequencies. After scientists and astronomers broke down the faint glimmers sent from the universe's earliest years, they discovered an unprecedented spike among the frequencies contained within the light. This was a crucial sign that the hot material around a black hole was beaming out slight traces of radiation across the universe. And yet, how black holes came to be spread across our young cosmos remains a mystery. Now, several teams of scientists and astronomers are always on the hunt to discover younger and hypothesized primordial black holes which formed after, according to some theories, before the Big Bang, but so far they remained elusive. That pushed researchers to work alongside the team that built the mid-infrared instrument to check for a stronger signature of the light from a distant galaxy. They did this in order to find other clues about how the strange black hole formed at the center of our universe and if they could make other discoveries. Another team, on the other hand, continued using the James Webb Telescope to make more findings about black holes, especially supermassive ones, after finding the universe's oldest black hole. The JWST found another supermassive black hole comprising something astronomers and scientists never expected. The world's most powerful telescope found carbon-bearing molecules called polycyclic aromatic hydrocarbons, PAHs, in the middle of 3 active galaxies. Finding these carbon-bearing molecules was not the only thing that baffled scientists, though. The location where they found them was what shocked them most. These carbon-bearing molecules were discovered where scientists didn't expect these molecules could survive. Also, observations from the molecules showed that the radiation around the supermassive black holes in these galaxies has changed the PAH's compositions completely. This could complicate a prominent technique astronomers use to calculate star formation and affect their usefulness as biological building blocks. Ismail Garcia Burnett, an astrophysicist at Oxford University in the UK, led a team of astronomers who studied observations of 3 active galaxies gathered by JWST's mid-infrared instrument. The 3 galaxies are NGC 6552, NGC 7319, and the popular Stephan's Quintet, located about 311 million light-years away in Pegasus, and NGC 7469, which is also around Pegasus, but at a distance of about 200 million light-years. PAHs are molecules that comprise rings of carbon atoms. These rings of carbon atoms are widespread in our universe as they're found everywhere, ranging from comets in our own solar system to distant galaxies. Their ubiquity is what makes them essential building blocks for life, but at the same time, it makes them vital traces for star formation. PAHs emit strongly at infrared wavelengths that can be found by MIRI when they're illuminated by the ultraviolet radiation in starlight. So anytime astronomers and scientists find PAHs this way, there are certainly young hot stars nearby. Garcia Burnett aimed to determine if PAH's emanation in the dense ultraviolet-rich environment in the middle of an active galaxy was the same as PAH emissions in calmer star-forming areas in the spiral arms of galaxies. While stars can form in the cores of active galaxies, the gas falling onto a supermassive black hole can also emit streams of ultraviolet light that make the PAHs glow. Previous models had postulated that the harsh radiation around the supermassive black hole at the core of an active galaxy would damage all PAH molecules. Instead, MIRI found out that PAHs were more in the central areas of all 3 galaxies that were observed. However, the analysis showed that the emission was coming from more significant and electrically neutral PAH molecules, which showed that radiation had indeed eradicated smaller electrically charged PAHs. The bigger PAH molecules may have survived the ordeal because they were covered by dense enveloping clouds of molecular gas. The loss of these smaller electrically charged PAHs is an issue for astronomers using these compounds to find clues for star formation. These star-forming areas are always mostly more affluent and electrically charged PAHs. If they turned out to be damaged in the cores of active galaxies, scientists and astronomers would be unable to find where stars might be forming. The next step is to analyze a larger sample of active galaxies with different properties, Garcia Burnett said in a statement. This will enable us to better understand how PAH molecules survive and which are their specific properties in the nuclear region of galaxies. Such knowledge is key to using PAHs as an accurate tool for characterizing the amount of star formation in galaxies and how galaxies evolve over time. Speaking of evolution, scientists and astronomers were not satisfied with these discoveries, so they kept pushing for more findings that would answer phenomena. One such phenomena is the singularity at the center of a black hole, the ultimate no man's land. It's a place where matter is flattened to an endless tiny point and all perception about space and time completely breaks down. But the singularity doesn't really exist, so scientists had to find something to replace the singularity. That birthed an array of possibilities. The first possibility was that matter doesn't get compressed down to an infinitely tiny point inside a black hole. Instead, there could be the tiniest possible configuration of matter, the smallest possible pocket of volume. This is referred to as a Planck star. It is a theoretical possibility envisioned by loop quantum gravity, which is itself a highly hypothetical proposal for creating a quantum version of gravity. In the world of loop quantum gravity, space and time are quantized. The universe around us is composed of tiny, discrete chunks, but at such an incredibly tiny scale that our movements appear smooth and continuous. This theoretical chunkiness of space-time provides two benefits. One, it takes the dream of quantum mechanics to its ultimate conclusion, naturally explaining gravity, and two, it makes it impossible for singularities to form inside black holes. As matter squishes down under the immense gravitational weight of a collapsing star, it meets resistance. The discreteness of space-time prevents matter from reaching anything smaller than the Planck length, around 1.68 times 10 to the power of minus 35 meters. So all the material that has ever fallen into the black hole gets compressed into a ball smaller than this, perfectly microscopic but definitely not infinitely tiny. This resistance to continued compression eventually forces the material to uncollapse, that is, explode, making black holes only temporary objects. But because of the extreme time dilation effects around black holes, from our perspective in the outside universe, it takes billions, even trillions of years before they go boom, so we're all safe for now. Another possibility looking to debunk the concept of the singularity is the gravastar, and this possibility does not depend on untested theories of quantum gravity, but there is a difference. The difference between a gravastar and a black hole is that the gravastar is full of dark energy instead of a singularity. Dark energy is a substance that penetrates space-time, therefore causing it to expand outward. Now, this concept might seem like something that happens in science fiction, but it's actually a real phenomenon. In fact, as we speak, dark energy is operating in the larger cosmos and is causing the entire universe to accelerate in its expansion. When matter falls on a gravastar, it isn't able to access the event horizon due to all that dark energy lodged in it, as a result leaving it to just exist on the surface. However, gravastars look and act like normal black holes outside that surface. A black hole's event horizon is its point of no return, the boundary beyond which nothing can escape, not even light. And as scientists continued to explore and reaffirm new phenomena, an observation was made about merging black holes with gravitational wave detectors. The outcome cancelled out the existence of gravastars because merging gravastars will give a different signal than merging black holes. Also, outfits like the Laser Interferometer Gravitational Wave Observatory and Virgo are getting more examples as each day passes. So while gravastars are not exactly a no-go in our universe, they are definitely on thin ice. Planck stars and gravastars may have remarkable names, but the authenticity of their existence is quite shaky. So maybe there's a more typical explanation for singularities, one that's based on a more realistic and nuanced view of black holes in our universe. The idea of a single point of infinite density comes from our perception of stationary, uncharged, non-rotating, and rather boring black holes. However, actual black holes are very interesting characters of space in their entirety, mainly when they rotate. A rotating black hole's spin stretches the singularity into a ring form. And according to the only math we've got, which is the math of Einstein's general theory of relativity, once you pass through the ring singularity, you enter a wormhole and exit from a white hole. This is the polar opposite of a black hole, a place where absolutely nothing can penetrate and matter rushes out into a completely new and existing patch of the universe at the speed of light. However, there turns out to be a challenge with this theoretical possibility. The The insides of these spinning black holes are devastatingly unstable, and this is according to the very same math that leads to the prediction of the traveling to a new universe stuff. The problem with rotating black holes is that, well, they rotate. This is because the singularity stretched into a ring is spinning at such an incredible pace that it has remarkable centrifugal force, and in general relativity, strong enough centrifugal forces act like anti-gravity. They push, not pull. This creates a boundary inside the black hole called the inner horizon. Outside this region, radiation falls inward toward the singularity, compelled by the extreme gravitational pull. The radiation is pushed by the anti-gravity near the ring singularity, and the turning point is the inner horizon. If you were to come in contact with the inner horizon, you would encounter a wall of infinitely energetic radiation. Basically, this means the entire past history of our universe would be blasted into your face in less than a blink of an eye. And this formation of an inner horizon sows the seeds for the destruction of the black hole. But rotating black holes certainly exist in our universe, which tells us that our math is wrong or something funky is happening. And that brings us to another weird question. According to the math of Einstein's theory of general relativity, once you pass through the ring singularity, you enter a wormhole and pop out through a white hole. So does that mean black holes are channels for perhaps space and time travel? Well, let's review that. Over the years, scientists have examined the possibility that black holes could be wormholes to other galaxies. As some have suggested, they may even be a path to another universe. Such an idea has been floating around for some time. Einstein teamed up with Nathan Rosen to theorize bridges connecting 2 points in space-time in 1935, but it gained some fresh ground in the 1980s when physicist Kip Thorne, one of the world's leading experts on the astrophysical implications of Einstein's general theory of relativity, raised a discussion about whether objects could physically travel through them. But it doesn't seem likely that wormholes exist. Indeed, Thorne, who lent his expert advice to the production team for the Hollywood movie Interstellar, wrote, "We see no objects in our universe that could become wormholes as they age." In his book, The Science of Interstellar, Thorne said that journeys through these theoretical tunnels would most likely remain science fiction. There is certainly no concrete evidence that a black hole could allow for such a passage. Not all scientists and astronomers accept that, though, because if black holes lead to another part of a galaxy or another universe, there would need to be something opposite to them on the other side. So could this be a white hole? A theory by Russian cosmologist Igor Novikov in 1964. Novikov proposed that a black hole links to a white hole that existed in the past. Unlike a black hole, a white hole will allow light and matter to leave, but light and matter will not be able to enter. Scientists have kept exploring the potential connection between white and black holes, and a 2014 study published in the journal Physical Review D explains it in full detail. Physicists Hal M. Haggard and Carlo Rovelli noted in the study that there is a classic metric satisfying the Einstein equations outside a finite space-time region where matter collapses into a black hole and then emerges from a white hole. In other words, every form of material that is being swallowed by a black hole could be spewed out, and black holes may become white when they die. Far from destroying the information it absorbs, a black hole's collapse would be halted. Instead, it would experience a quantum bounce, therefore enabling information to escape. Suppose this turns out to be the case. In that case, it will shed some light on a proposal by former Cambridge University cosmologist and theoretical physicist Stephen Hawking, who in the 1970s explored the possibility that black holes emit particles and radiation, thermal heat, as a result of quantum fluctuations. Hawking said a black hole doesn't last forever. Finkbeiner noted, Hawking proposed that the radiation would instigate a black hole to lose energy and shrink and disappear. This was what he described in his 1976 paper published in Physical Review D. Based on his claims that the radiation discharged would be random and comprise no data about what had fallen in the black hole, it would take along with it loads of information upon its explosion. This also meant another thing. Hawking's idea did not go hand in hand with quantum theory, which states information can't be destroyed. Physics states information becomes more difficult to find because if by chance it becomes lost, it would be impossible to determine the past or future. Hawking's idea took the entire world of science down to the black hole information paradox, and it has puzzled scientists since then. In fact, some scientists and astronomers have noted that Hawking was simply wrong, and the man himself even said he had made a mistake when he attended a scientific conference in 2004. So should we return to the concept of black holes emanating preserved information and throwing it back out via a white hole? Perhaps we will. In their 2013 study published in Physical Review Letters, Rodolfo Gambini at the University of the Republic in Montevideo, Uruguay, and Jorge Pullin at Louisiana State University applied loop quantum gravity to a black hole. From this activity, they discovered that gravity doubled towards the core but reduced and plonked whatever was penetrating another area of the universe. The results gave more credence to the idea of black holes being a portal. In this study, singularity does not exist, so it doesn't form an impenetrable barrier that crushes whatever it encounters. It also means that information doesn't disappear. Yet, physicists like Joseph Polchinski, Ahmed Al-Mahiri, Don Marolf, and James Sully still believed Hawking could have been onto something, so they worked together and came up with a theory known as the black hole firewall hypothesis, or the AMPS firewall. By their calculations, quantum mechanics could feasibly turn the event horizon into a giant wall of fire, and anything coming into contact would burn in an instant. In that sense, black holes lead nowhere because nothing could ever get inside. However, this contradicts Einstein's general theory of relativity. Someone crossing the event horizon is not supposed to feel any form of great hardship because a person or an object would be in free fall. Based on the equivalence principle, that person or object would not feel the intense effects of gravity in any way. It could follow the laws of physics present elsewhere in the universe. Still, even if it didn't violate Einstein's principle, it would underestimate the quantum field theory or suggest information could be lost. So now the entire theory of what a black hole comprises and where it leads to has left the entire world of science and astronomy in a dilemma. But from your own perspective, what do you think? Is something really in these black holes, and do they lead to a place scientists and astronomers haven't discovered yet? Let us know in the comments section below.